Welcome back to Applications of Derivatives here, and again feel free to subscribe. I'm going to talk to you now about the second derivative test. Now, we generally talk about the first derivative test, and we talk about concavity, and we talk about the second derivative test, and then students think that that has to do with concavity. It does have to do with concavity, but when you're using the second derivative test, you're actually using it for the same thing you used the first derivative test for. It's used to determine extrema. So we're looking for extrema using the second derivative test. Now, to apply the second derivative test, you actually have to do, you need to have the function, you need to have the first derivative, and you need to have the second derivative. So all three play a role here. So what you need the function for? Well, you need the function to determine what the actual extrema are, what the y values are. What do you need the first derivative for? Well, you need the first derivative so that you can set it equal to 0 and find your critical numbers. And then what do you need the second derivative for? Well, you need it to apply the test. Because it turns out if the second derivative is positive at a critical number, then the function has a relative minimum at that critical number. And if the derivative is negative at a critical number, then the function has a relative maximum at the critical number. Now make sure you realize what we're saying here. Second derivative is positive, relative min. Second derivative is negative, relative max. Okay, and there is a reason for that, but I'm not going to go over that in here. You can probably just Google it, why the second derivative test works or something like that, and you'll probably find a video that explains it to you. All right, now if the second derivative turns out to be 0 at the critical number, then the test fails and you have to go back to the first derivative test to determine. Now if the test fails, it doesn't mean it has an extrema or it doesn't have an extrema. You've got to go back to the first derivative test. Now you can pause the video and read the rest of this thoroughly, but I'm going to go ahead and move on in to show you how to apply the second derivative test. So the first example here, I have f of x equals 3x to the fifth minus 5x cubed. And I want to apply the second derivative test. So the first thing I need to do is I need to find the critical numbers. So I calculate the first derivative, which is 15x to the fourth minus 15x squared. Then I set that derivative equal to 0. I factor it, and then I set those factors equal to 0. And I get the critical numbers from those factors, -1, 0, and 1. Now, I need the second derivative to test. So I need to find the derivative of 15x to the fourth minus 15x squared to get the second derivative. Well, just apply the rules for differentiation. The derivative of this would be 60x cubed, and the derivative of this would be minus 30x. And now, we take each critical number and plug it into the second derivative. So if I plug -1 into the second derivative, I get 60 times -1, which is minus 60, and then minus 30 times -1, which is plus 30. So I get minus 60 plus 30 is -30. So since the second derivative at -1 is less than 0, then that implies that f of -1 is a relative maximum. Okay? Now, let's evaluate the second derivative at 1. So if I plug 1 into the second derivative, I get 60 minus 30, which is a positive number. And so since the second derivative at 1 is positive, that implies that f of 1 is a relative minimum. And then if I evaluate it at 0, if I plug 0 into the second derivative, I get 0, and that means the test fails. So I must use this first derivative test. Okay, so you got to go back to the first derivative test. Now, go ahead and apply the first derivative test at 0. In other words, pick a number just to the left of 0 and plug it in, like -0.5, and then pick a number just to the right of 0 and plug it in to the first derivative. And you'll find that the first derivative has the same sign on both sides of 0. So that tells me that f of 0 is neither a relative max nor relative min. So all I have here is a relative max of -1 and f of -1, which f of -1 is 2, and then 1 and f of 1, which is f of 1 is -2. And again, I got the y values by plugging -1 and 1 into the original function. Now, this test works best on polynomials. Okay, now it's no fun if the test fails and you have to go back to the first derivative test, but it works on many polynomials without failure. Okay, let me show you what happens on this trig function. I'm going to look for extrema on this trig function only on 0 to pi. So here's what I'm going to do. I'm going to take the derivative of cosine x squared, and I'm going to get minus 2x times sine x squared. And then if I set that equal to 0, I'll get minus 2x equals 0, so x equals 0, that's one answer. And then if I say what sine of x squared equals 0, well, I know that sine of 0 is 0, sine of pi is 0, and sine of 2 pi is 0. Okay, so the critical numbers would be 0, square root of pi, square root of 2 pi, and square root of 3 pi. And that would be the numbers that are on the... Now I had to get a calculator and see how far I had to go out with these square roots. But it turned out that square root of 3 pi is just a little bit more than 3. And since pi is 3.14, square root of 3 pi falls within the range. But if you go out to square root of 4 pi, then that's going to be bigger than pi. So that's, you know, you can just skip that one. So we just get these numbers here. Now, those are my critical numbers. Now, I need to evaluate the second derivative. So to get the derivative, get the second derivative, I got to take the derivative of this function, and I just used the product rule, and when I got done, I got this. Okay. Now, I evaluated that at 0. When I evaluated at 0, I got 0, so the test failed. But x equals 0 is an endpoint anyway, so I could just determine, since the function is decreasing, f of 0 is actually what we call an endpoint relative max, because to the right of 0 the function's decreasing. The function's decreasing to the right of 0. Okay. Now, what about at square root of pi? Now, I had to use a calculator, so plug square root of pi into this function right here, and I ended up getting a positive number. So, since I got a positive number for the second derivative at square root of pi, then f of square root of pi is a relative min. What about square root of 2 pi? Well, when I put square root of 2 pi in here, I actually ended up getting a negative number, and so since the second derivative evaluated at square root of 2 pi is a negative number, then f evaluated at square root of 2 pi is a relative max. And then I finally had to do 3 pi, so I evaluate the second derivative at square root of 3 pi, and when I plug that in, I got a positive number, so therefore f evaluated at square root of 3 pi is a relative min. Okay, so you can see it. That was definitely not fun. That's why I said it's best to do this on best to only use this method if you have polynomial functions. Okay, now here's the graph of the first one. Notice the graph of the first one. We got a relative max there. We got a relative min there. And notice right here we got a horizontal tangent line. That's why 0 was a critical number. But we didn't get a extrema there because it just continues to decrease as you go through there. All right. Now on this one, I think, let's see, here's 0. So there, see, it's a relative max because it's decreasing on this side. So it's an endpoint max. And then as you go down through here, this is square root of pi. And so notice that at square root of pi, you get a minimum. And then square root of 2 pi, that's that number, you get a maximum. And then square root of 3 pi, you get a minimum. And of course, this is pi. And pi, I guess I could say pi you get an endpoint minimum there. I didn't say that, but you know, you get an endpoint minimum there at pi. Okay, so now here are some practice problems that you can practice on here for the second derivative test. This one, again, find the critical numbers, which is 1. Evaluate the second derivative at the critical number, and since the second derivative at the critical number was positive, then f of that number is actually a relative minimum. And you can see there's the picture there, and there's the minimum. And then here, take this one, find the critical numbers by setting it equal to 0. Now this one, by taking the derivative and setting it equal to 0, this one, when I solved it, I got 0, square root of 3, and minus square root of 3 for my critical numbers. And this one actually worked out good, because when I plugged 0 into the second derivative, remember you need the second derivative to test it. So when I plugged 0 into the second derivative, I got negative, so that means f of 0 is a relative max, and you can see that that would be that point there. And then at square root of 3, I got a positive number for the second derivative, so that means I get a relative min. And let's see, that would be this point over here. And then at minus square root of 3, I also get a positive number, so I get another relative min over here. Okay. And then this last one here, again, this one kind of shows you why you might not want to use the second derivative test on this one, since this is a quotient. But the only critical number you got was 0, and if you evaluate, it's kind of hard to get the second derivative, but if you do evaluate the second derivative at that number, you actually get a negative number, which implies that f of 0 is actually a max, and that's that point right there. Okay. Again, I'm going to use this test, but maybe I shouldn't, because really the first derivative test is probably better on a trig function. But remember earlier we found the critical numbers for that function was pi over 4 and 5 pi over 4. So you can easily show that the second derivative is minus cosine x minus sine x, and then just evaluate the second derivative at pi over 4, and I got a negative number, so that means the function has a relative max at pi over 4. And if I evaluate at 5 pi over 4, I actually got a positive number, so that means that the function has a relative min at x equal 5 pi over 4. And that's pretty much it on the second derivative test. On the next videos, I'm going to show you how to use everything we've learned in this section on application of derivatives in order to sketch graphs. So I'll see you there.